Hello, everyone. My name is Luan. Today in this session, I will be presenting this paper, full in LIME and SHAP, Adversarial Attacks on Post-hoc Explanation Methods. This is a short paper, but the idea is very interesting. The main objective is to show that the post-hoc methods like LIME and SHAP that try to explain individual predictions of the black box model can be fooled and detect bias in models. So for this, they create a framework. So they create a framework that manipulates the outputs of the models and on a way that's final the final results of this framework is equal to the bias model and in the real data, but the predictions, the explainability tools like LIME and SHAP cannot detect the bias that the model is having. So quick explanation on the main things of LIME and SHAP that are common techniques like of interpret individual predictions, and both of them have in common that they use perturbations on the original inputs of the data to try to see how the model behaves, and with this apply some technique on this generate data so that he can detect like some feature importance for each prediction of the model based on the space that they are the space feature they are. Here, like in the right side, we can see like a picture that is in the paper that they use this COMPAS datasets, original COMPAS dataset. They reduce it using PCA for 2 dimensions to show how these new generated points are formed, can be viewed. Like in the blue dots, we can see the original data. They are from words, real words, data, and the orange one is perturbation made by the LIME that they use like noises to get the original data and create noise in each feature, so they can plot like these different data points across the original distribution of the data, and later on try to get the feature importance. And now we can see here, this will be important in the future, that we can distinguish pretty clearly the data points that are created for the line and the data points that are real from the base. So here they will construct what is called adversarial attack, so that they can construct this bias classifier F, show F, that they will be full like some regulation or some user that wants to take this model and see if there is some bias or anything else. So for this the adversary, let's call this guy that wants to hide this bias in this model, they need to provide a model and that inputs data sets to use it to train this model, and in which the model will be applied, and sorry, and for the final objective of this adversary is to create a framework that you behave exactly as the original model that they create, so that the inputs of the real data will output the original model outputs with the bias that the adversary wants, but the techniques imply that will be tested here, LIME and SHAP, will not detect this bias on the line in this model. So for creating this adversary classifier, they will utilize the effects of the perturbations that we talked earlier, so that they can detect these perturbations and that the LIME and the SHAP creates, and detect these points that are used for them, and then outputs different values based on if there is a real data or if it is a, points created by these techniques. Like for instance, here he will get the x, the data point that he wants to predict, and if the data belongs to this distribution, the original distribution of of the the real worlds, they will utilize the model, the bias model, to make the prediction. But if somehow he detects the distribution is wrong, is from the uh, created one by the LIME and SHAP, they utilize a uh, Sigma model that will not be biased. This will create another rules and another model for this. Going to the experiments, so I will explain better how they do this. They use like 3 data sets, the COMPAS. There are say the risk that a guy needs to have like to reinstate in the in jail. The community crime, they are the crime rates on different areas, and the German credits. In these three data sets, there are sensitive features among them, like race in the COMPAS and the community crimes, and gender in the German credits. For making the adversary classifier, they need to create the F, as we discussed later, the model F that will be biased, and for this they create a model that specifically make the prediction specifically in the race, in the case of the COMPAS in the community. If they, in the case of COMPAS, for instance, if they are African American, they will predict that they have a high risk of reinstate in the in prison. And for German credits, if they are male, they have like a better chance to be a good customer. And for the Sigma model, they will be using 2 different ways, using uncorrelated data with the sensitive features. In the case of the COMPAS and the community crime, they use synthetic data that they create. In this case, if we look into the GitHub, they utilize simple random selection to make this decision if the guy is, if there is a high risk or if the neighbor is violent and everything. And for the German credits, they utilize the gender for the F, and for the Sigma, they uses the, I believe is the loan rate as percentage of income. So in this way, they will be having two different these 2 different models. So in the next steps, from then, as we discussed, is to detect the new what there are points that are distinct, that are not from the original distribution, and the points that are original from distribution. For this, they create a model for classify this by creating a data set. I didn't write this, sorry. They create a data set on, they create the perturbation for each type of technique. For instance, the LIME, they will create a perturbation, they will create noise in each feature, and then from this they create the new points, and then they get like these new points and the points that are original, create the labels, and run a model to detect, to make the predictions if the points that are given for the model is, for the framework, is from the original data set or is a perturbated one. In the same way they do it for SHAP. The only difference in the SHAP is that the SHAP don't use perturbation in the noisy features. So they utilize like they sample a subset of features, and for the features that are not setted, they utilize the background distribution determined by the k-means models to different groups. And from this, they can make a model that can classify if the distributions are different, if the points that are given for them are from different type of, if they are from the original distribution or they are some data that was created by this technique. Based on this, if they are from the original model, they run the F model, and if they don't, they will run the sigma one. Like going through some results of the get-it, just like from this COMPAS feature, the COMPAS dataset that they used. This here in the x-axis, we have like the percentage for each bar is like the first more important, the second more important, the third more important feature, and how much each color represents one feature, and how many of data points they are classified as the importance. So, for instance, in the left here, using LIME, this is the bias classifier, the one that is not like, there is no passing by framework. The LIME accurately detects that the African America is the primary and maybe only feature that we'll be using to say if this guy will go back to prison or not. And once they use the attack using the attack online, using one feature, one synthetic feature that they create using simple random frame, we can see that like 100% of the features that the points that was like first detected as African America, the most important features, now they are not anymore. So like there is a huge misunderstanding of the line on what is giving this information. And the same way we can see with two features here, they create two synthetic data and using just if one of them is one, they predict as one of the classes, and if no one of them is one, they predict it's an XOR. So we can see two in the chap that similar behave occur, but in a less preeminent form, as the bias classifier in the same way is detected that only the first one, only the African American is giving the decision, but with the attack with one feature, most of the first class is clean of African America. With the second one, we see a better, more even distribution between the first, second, and third one that we don't see the first one. But these two less inclined things must be because of they point out that must be because the SHAP tried to is a added one, right? All features have some weight in the explanation. What is not true for LIME. LIME gives a number between 0 and 1 through each feature. But for SHAP, they try to distribute among all features what will be the feature importance. With the fooling, they are kind of distributing evenly between the features. But they can definitely, in both of the cases, they definitely have the change, and they are being like mistakenly put other features that don't have no importance for the original model in this. So in the last point, one thing that is really important on this type of thing is the vulnerability of its technique on the detection of if the data point is from the original data set, or if the data point is from perturbation on the original dataset. You can see here, for instance, that the line is like less vulnerable. We need to have a more precise model because he started to drop out. He only with the F1 score of the classifier to detect if the point is out of distribution is like closer to 0.8. They can detect they start to decrease the performance. They start to get right the explanation as being the race. And for the SHAP, they start to decrease less. They don't need to be very accurate, but they have like a smoother curve. Should they be completely wrong, the classifier must be really, really good. That is not true with the line. Once they reach some thresholds, the line starts to get everything wrong. This is basically the experiment that they did. So they made other experiments in other things, but the major conclusion is that in all of them, they was decreasing in the way that the correctness of the LIME and SHAP to detecting the correct feature that was making these predictions. And they are basically, just because they are vulnerable to see if these features are out of distribution or not. They are too much reliable on this, and they let this pass through too much. And basically, one of the primary conclusions of these guys are that there may be another ways of doing this, or to make this more robust to this type of attack, or to new techniques. But this is basically what I wanted to show to you guys. It's a short paper, and if anyone wants some questions or some comments, we can see.
Nice presentation. I think the topic is very interesting, right? How it's able to, of course, I think one point is like, we cannot trust blindly, right? Like these methods, but also is because they create an adversarial attack, right? Which is kind
Yeah,
of, so maybe that, the main issues wouldn't happen if, like if we didn't apply anything, right? Or maybe how we model, right, some features, right? I think maybe that could be could be like maybe not that we wanted, but maybe we even apply something that could impact the model, not the model, but how we see, like, perceive the features, right? But yeah, I think it's really interesting. And what do you think? Why did you choose this paper? I think because I think it's a very interesting topic, right? Because these methods, right, is like, how we can better understand our predictions, like explainable AI. But also, I think there's a paper from Jessica, right, from last year that talk a bit about that. These methods don't agree every time, right? So maybe they will reason in some way, like how they got to a result, and they will differ, like on the features, right? But also, it's your paper also shows that maybe some information can be hidden without too much uh, decrease in performance. Not in performance, but like, it's the model, and then it doesn't show some obvious bias in some variables, right?
one of the things that this type of techniques rely on is in the distribution that we furnish, give the data, right? So if we get like a sample that are out of this distribution, completely new to the model and completely new to the detection as well, they can completely miss what is giving the information. So this can be just because like there is a different type of person, or the selection of the training of the model is wrong, was not doing correctly. And this can also be using the other way around, because someone can exploit this to pass some information through, okay, oh, I get this like just a little bit out of they are used to, so I can bypass the thing, so like think something that is fraudster. A fraudsters know how they should behave. They go out a little bit of the curve, and the model can detect. We can't not know how this guy are, because he cannot explain this. The model can't explain this.
Yeah, and also how to fool regulatory agents,
Yeah.
maybe, right? Because you have like credit and I don't know. I think the example of the paper, right? So, oh, maybe a regulatory agent would like to understand how you got that you denied credit for this person or not. And they're like, the guy's like, I don't want to lend money to this specific group, but I can't be obvious on that because there's some regulatory agent. I don't know. Maybe that would be like the worst case scenario, right? I think
Yeah.
the paper even said, "Oh, could be very badly used." I hope that this doesn't happen too often, at least, right? But yeah, it could be
Probably
used, right?
happens.
But yeah, like it's really like this, because this is also we are using from the model, right? The perturbations line to try to gauge like how and why did it got like some classification, right? So even it's not a perfect model, right? But sometimes it's used, right? So like, oh, use SHAP to get the feature importance and stuff like that, right? But yeah, really interesting. Any other comments or questions for Luan, guys?
First, congrats. Very interesting
Thank
paper.
you.
The one thing that I was just a comment with like that with regulatory like landscaping AI evolving very fast. I believe that like we will see an standardization of bias checking models, like credit models, this kind of thing. And I would say that today one of the most common contenders for this would be SHAP and LIME, for example. So that's why I think it's very interesting because like this would be like an ill-intentioned agent would be able to hide the true important features in their model. Of course, there would be regulations regarding like, no, race can't be a can't be a
A
feature.
feature.
Yeah,
This
this
would
is
be a good one.
already quite messed up. But
Yeah.
for example, let's say models that governments use to approve passports. This is definitely will be a thing, right?
Mhm.
Someday in the future, and maybe race could be a feature of those. And just
And this
very
is a simplify with using one feature, but this can be like multiple features that are correlated with each other and end up in being biased. This can be like will be more complex, but this can be done to with the same logic.
mhm. Yeah, they're like very interesting. And we will see a standardization of explainability for black box models. This will happen because else, like, nobody will be for blocking black box models of providing important decisions because they just perform way too well. And I believe that we are and not jumping to the hype, but just saying like from the current state of investment, we are more closer to AGI than to neural networks real explainability, right? So
Mm-hmm.
in terms of like the amount of money being invested in each one of the research topics, this is a very interesting, and also it's good for us that we lend money, we block card transactions, and we gotta keep this in mind.
Once regulation is up, this will be pushed. One thing that interesting too, because like this is not only by is an important topic by fooling things or regulatory, but like there is like uh, more sensitive things like medical, that there is not only the results that is important, but why that we don't have like very good techniques yet. This is very interesting. Looking forward.
Yeah, but that could be also right for what's the name? Jesus, the seguro insurance, right?
Yeah.
That could be something, right? Oh, I don't want to insurance this type of profile like that, and that's really, I don't know, or that would like impact like how the value, right, of the policy. Yeah.
Mm-hmm.
There's this thing where there was like a magical thing, like I believe that was cancer detection, that they were using this method, like they were trying to detect cancer, and like they got a very good performance in the training. So it's like, wow, they're doing very well. But on production, it went very badly, and they discovered after a long time that one of the training amount of training samples that they had a different border in the image, which were from older cases, and the older cases were all positive. So they were actually putting in production like a human killer. Yes.
A border detector.
Yes, the border detector, and they were like going to tell everybody like that was this border was from old samples. The new samples were all like negative, and they would be telling nobody had cancer. So if I remember correctly, right? But this is
Oh,
very
there's very funny cases like this. I remember when showing line on images, there was a case that like, oh, it's a wolf or dog detector, right? And the model performed well to detecting dogs and wolves, which is kind of challenging, right? But then they looked into why the Lime was no why the model was classifying using Lime, and Lime for images it highlights like the pixels, right, or the image that shows the areas that led to the classification in some way, right? And then they saw the pictures of the wolves. It was not detecting features of the wolves, like maybe the snout is larger or the tail is different. They were detecting the background because the pictures of the wolves were in the snow. So it was detecting snow. Oh, there is snow, wolf. If not, dog. So yeah, which I think is why it's so important to have like some error analysis later, right? So you can try to find some this why some weird stuff happens.